Welcome, one and all, to Limits and Continuity, the highly anticipated, long-awaited sequel of Prerequisites for Calculus. This is basically just Chapter 2 in your textbook, whereas Prerequisites was Chapter 1. Anyway, this series is probably going to be a little bit shorter than the last one, simply because you were introduced to it much more in pre-calc, and there's a lot more in your textbook about this than the prerequisite stuff. This one, for example, this video, the formal definition of a limit, you aren't really going to need to know this. This is just first in this series because it was first in our textbook. It was one of the many formulas you'll come across this year where your eyes just glaze over and you skip it out of boredom, which I totally understand. But this is just going to give you a little bit of enrichment and intuition behind the basis of calculus, aka the limit. But after this, I'll be making stuff about solving limits, stuff about the intermediate value theorem, and a video about the definition of a derivative. So before I get to all the symbols and letters and whatever of the formal definition, let's figure out the intuitive thing that you're normally taught in the beginning. This is much easier to understand. There's nothing wrong with this, but it's not very mathematical in terms of how rigorously everything is defined. So if I have a function, there's my curve. Oh, there's a discontinuity. What do you know? If I want to find the evaluation of the limit as x approaches a, that's just any number. As x approaches a, what does f of x approach? Well, it approaches some limit L, right? F of x isn't defined at that point, but it still has a limit because you can visually see that these values, as you get closer and closer to that discontinuity, as you get closer and closer to that, they're approaching y values closer and closer to L. The other way you could visualize that is if I had a graph of x and f of x, let's say a equals 5, just for our purposes. So say I plug in a 6. Oh, I would get some f of x that's, not very close to our limit L, but, kind of close. Then we go to 5.1. That's a little bit closer. Then we go 5.01. Even closer. And then you can keep doing that until you notice that these output values approach L, some number. And it's apparent if you have an actual function. I just drew a squiggly line. But anyway, you've been introduced to this several times, I'm sure. But that's the intuition that you have initially. Alright, now we're ready to build our understanding of a formal definition of a limit. So, this is our intuitive understanding, right? As x gets close to a, as we get closer and closer to a, y approaches L. That's our intuitive understanding. So we said a limit exists when, as x gets close to a, f of x gets close to L. This is the same thing, but a little bit more wordy. So a limit exists now in this new definition if you can get f of x as close as you want to L by making x sufficiently close to a. So let's try and just do that with this graph. So you can get f of x as close as you want. I crossed it out. As close as you want. So if I want to be this far away from L, this distance right here, I want to be that far away from L. What this is now saying is that I can pick x values sufficiently close to A so that I will always have f of x values as close as you want to L. So you see this little interval around L? Within this is how close you want it to be to L. So I want to be within this distance from L. I'd say, okay, I'll give you a range around A that corresponds to this range around L, so that if you pick any x in this range, you'll get an output value that is always in your range around L. So if I want to be this far away from L, what x values would I pick to guarantee, right? Sufficiently close means I would guarantee you that every x value in that interval would be close enough to L. So the easiest way to do that is just draw a line straight down. And this right here is our new distance, our new x distance, sufficiently close to A, so that if you pick any x value in here, say I pick an x value in this interval. I'll pick an x value here. So you want to be within this distance from L. Well, if I pick an x value here, you will be that close to L, right? And if I pick an x value here, you will be that close to L. All these output values in this whole interval, if you map all of those to all of these output values, it will always be within your desired range of L. I want to be that close to L, and I said, okay, you have to be this close to A to be that close to L. Alright, now I took it a step even further than this. So now I made it a question and an answer. So these two, all these are still the same, but this is just taking it a step further. So how close do you want to be to L? This is this range around L. That's how close you said you wanted to be. And I found you another number, this distance right here, another number, whatever that is, away from A, so that it guaranteed your specifications. This is what your specifications were. You said, I want to be within this from L. I want to be within that distance from L. And I said, okay, if you're this distance from A, you'll always, if you're in that interval, if you pick x values in that interval, you'll always have output values within the range that you wanted. But these numbers, they also have names. They're any number, but they are variables that come from the formal definition of a limit. So this is how close you want to be to L. It's just epsilon. So I want to be epsilon away from L in either direction, right? This distance here is epsilon, this distance here is epsilon. And then I'd say, okay, I'll get you within epsilon away from L by finding you another number, delta, around A. This distance is delta, this distance is delta. That guarantees you that you will always have something within epsilon of L. And now I just put in the actual x and the y values so that you can see it easier. So if I'm delta away from A, this distance here is A plus delta, that's A minus delta. This distance, total distance, this is supposed to be over here, sorry. This total distance is delta, and this total distance is delta. Same thing up here, epsilon away is epsilon up or epsilon down. And now we just took it to the final step. So this is the same as this is the same as this is the same as this. Now we have just more mathy, but the exact same thing we've been talking about this whole time. So given a positive epsilon, so that translates from this. So you get f of x as close as you want to L, and I'll give you a range around A, so that if you pick any x in that range, you'll always be that close to L. So you can get f of x as close as you want to L. That distance is epsilon. So given a positive epsilon, that just means a positive distance away from L. Maybe it's 0.01. I want to be within 0.01 of L. There is a positive delta, that's that range around A, so that if, and then this is the normally confusing part, this is just saying, so that if I give you a range around A that is within delta, greater than 0 but less than delta, it corresponds to your desired epsilon, giving you y values or f of x values within epsilon of L. Now I'll go to a quick sidebar to kind of explain this a little bit further, and then hopefully you'll have all the tools that you need. Alright, the last thing we're going to look at before we tie it all together is how the absolute value kind of fits into everything. So if you subtract any two numbers, let's just do an example, a minus b. If you subtract any two numbers and put absolute value around them, that is saying the same thing as what is the distance between the two numbers on a number line. So if I pick the numbers -2 and 5 and I put those on a number line, and I ask you what's the distance between -2 and 5, you could do -2 minus 5, but that's -7. And like in geometry, if you have a negative area or a negative perimeter, that doesn't really make any sense. So a negative distance is not what we want in this case. So that's the reason for the absolute value. And if you did 5 minus -2, that would also be 7. So the distance between -2 and 5, you can take either one, a minus b or b minus a. Take the absolute value, that is the distance between the two. So if we look up here, f of x minus L and absolute value, the distance between f of x and L, and this is the distance between x and a. with that, now we can look at this more in context. So what this is saying now is the distance between x and a is less than delta. And this is saying the distance between f of x and L is less than epsilon. So if epsilon is our desired distance away from L, right, we want to be within epsilon of L. Within epsilon of L is saying I want to be the distance from L that I want to be, the distance from L that I want to be, that's what this is saying, is less than epsilon. I want to be within epsilon of L. So if I have any y value or any f of x value, the distance between that and the limit value should be less than epsilon, and that should guarantee us that we will be within epsilon of L. So this right here, if we chose that as our f of x, well, the distance between L and that is obviously smaller than the distance between L and that, and this whole distance here, this whole distance here is epsilon, right? This distance here is epsilon, and this distance here is also epsilon. So we want to be within that. So as long as we pick y values, where the distance between the y value and L is less than epsilon, we can fill up this whole interval with f of x values that are our desired closeness to L. And then, if we remember, that corresponds to the distance from x and a being less than delta. So the same thing here, right? You said, I want to be this close to L. I want to be within epsilon of L. And that's what this is saying. The distance between f of x and L is less than epsilon. That's within epsilon. This is saying, if you pick any x away from a, that is less than the distance delta, so any distance between x and a, this is an x, this distance right here is less than delta. This whole distance right here is delta, and that is delta. So my distance has to be less than delta for any x value I choose, and if I choose any x value in that range, I will get you a y value within epsilon of L. So that's basically all the understanding you have to have. The last thing I'm going to say is that you often also see this right here, and all that's saying is that the distance between x and a has to be positive. So bear with me for a second. If you wanted to make this equal to 0, if you want to make this equal to 0, what would you do? Because the only thing you can change is actually x. So what you would do, you would make x equal to a, and then you would have a minus a. So a minus a, that's a plus. A minus a greater than 0. Well, now we have 0 is greater than 0, which that doesn't make any sense. And the other reason that doesn't work, if we chose x equals a, there's a. If we chose x equals a, and this is the whole thing with limits, maybe it's not even defined there. In this case, it's not defined there. So I can't choose an x value a because it doesn't exist. So with that, now we can actually go back to our formal definition and make sense of everything. So that is all that you have to know. Now let's just deconstruct what we've gone over so far. So we said f of x gets close to L, right? We get close and close and closer to L as x gets close to A. As we get close to A, we're getting y values closer and closer to L. So that was your intuition. And then we said, okay, a limit exists only when you can get f of x as close as you want to L, right? And then we define this as close as you want to be epsilon. We just called that epsilon. You can get f of x epsilon away from L by making x sufficiently close to A. So close enough to A to guarantee that any x I pick in my range around A, as long as x isn't A, will give me an output value in my epsilon away from L, in my range around L. So we said x sufficiently close to A is just delta away from A. So that's all that this is saying. It's not incredibly complicated. I really didn't understand it for a long time because all the symbols made literally no sense. But all it's saying is that, okay, I want to be epsilon away from L. Again, epsilon is any number. It could be the smallest number you could think of. I want to be that close to L. And then you would say, okay, I'll give you a delta, a range around A, such that if you pick any x in that range, it will always give you a y value in your desired distance away from L. So you can kind of see how this has nothing to do with the actual point being defined. So f of A doesn't have to be defined. Nothing with limits ever talks about that. It's just saying this window around our point, if you zoom that in and zoom that in and zoom that in, take your electron microscope, zoom it into that, you should still be able to find a range around A. If the limit exists, you should be able to find a range around A, so that if you pick any x in that range, you'll still get outputs around how far away you want it to be to L. So that's, if we go back up to our ugly looking definition, a limit, f of x has a limit L as x approaches A if given a positive epsilon, there's a positive delta, so that the distance between x and A is between 0 and delta, so that's just that, and it corresponds to the desired distance away from L. So given any epsilon, any positive epsilon, that's the epsilon you choose, that's how far away you want to be from L. I want to be 10 microns away from L. Alright, I'll give you a positive delta so that my range around A, that is less than delta away from A, will always give you an f of x that is no further from L than your epsilon, your desired distance. So it'll always be within your specified range. And that's all that the epsilon delta definition of a limit is.